Have you ever stopped to think about what's actually happening when you send a message, watch a video, or use a funny filter? It's all built on a secret language. And our journey into that language, well, it starts with a very strange sentence. So, this weird quote, it actually came from a chat app that had a voice changer. And it is the perfect example of digital magic, right? Taking one thing, your voice, and turning it into something completely different. But here's the thing, it's not actually magic. It's just a really clever set of rules. And that's the real question we're going to dig into. How does all the rich, complicated stuff from our world, our voices, our pictures, our words, get translated into the only thing a computer can actually understand? Just a long, long stream of zeros and ones. To get it, we have to start at the very, very bottom, with the smallest, most fundamental piece of information you can possibly imagine. Meet the bit. It's short for binary digit, and it's the atom of the digital world. A bit only has two states. It's either off, which we call a 0, or it's on, which we call a 1. That's it. Every single thing on your phone, your laptop, every video you stream, it's all just a massive, mind-boggling collection of these tiny, microscopic light switches. See, we humans grew up counting with 10 fingers, so our whole number system is based on 10 digits. We call it decimal, or base 10. But computers, they only have 2 fingers, on and off. So their system, called binary, is base 2, and that changes everything. So how in the world does a computer see a number like 13? Well, it thinks in powers of 2. 1, 2, 4, 8, 16, and so on. To make 13, it asks, what's the biggest power of 2 that fits? That'd be 8, so flip the 8 switch on. Okay, 13 minus 8, we have 5 left. What's the next one that fits? 4. Flip the 4 switch on. Now we have 1 left. The next switch, 2, is too big, so we'll leave that one off. And finally, the 1 switch fits perfectly, so we flip that on. So we have 1, 8, 1, 4, 0, 2s, and 1, 1. In binary, the number 13 is 1, 1, 0, 1. Now, one little bit by itself can't do much, so we group them together. The most common grouping is 8 bits, and we call that a byte. A byte is super important because with those 8 spots for zeros or ones, you can make 256 different combinations. That means a single byte can represent any number from 0 all the way up to 255. And from there, we just scale up. Kilobytes, megabytes, gigabytes, you know the drill. Okay, fine, so computers get numbers. But what about language? What about your text messages? How do you possibly turn the letter A into a bunch of light switches? Well, for that, we need a kind of digital decoder ring. The solution is something called character encoding. It's basically an agreement, a universal rulebook that we've all decided on. The rulebook says that every single letter, every symbol, every punctuation mark gets its own unique number. So when you type a character, the computer doesn't see a letter, it just looks up its number in the book. One of the very first rulebooks was called ASCII. And in the world of ASCII, a capital A is always the number 65. A B is 66, C is 67, and on and on. So when you type the word cab, your computer isn't seeing letters. It's just seeing the numbers 67, 65, and 66. Simple as that. But what happens when different computers are using different decoder rings? You've probably seen this before. ASCII was great for English, but it didn't have room for characters from other languages. So people invented new systems, like one called Big 5 for Chinese characters. But if your computer tried to read that text using the wrong system, you got this mess. That garbled text you sometimes see isn't random junk, it's just your computer reading the numbers from the wrong rulebook. Clearly, this was a huge problem. The world needed one single, universal decoder ring for everybody. And that's exactly what we got. It's called Unicode. Unicode is this massive, global standard that has a unique number for pretty much every character in every language on Earth. And yes, that includes all your favorite emojis. All right, so we've got numbers and letters down. But what about a photo? How do you capture the visual world, something that's smooth and continuous and infinitely detailed, and trap it in a finite set of zeros and ones? This gets at a really fundamental idea, the difference between analog and digital. The real world is analog. Think of a sound wave or the smooth gradient of a sunset. It's all continuous. A digital version has to chop that smoothness up into little countable pieces. It's not the real thing. It's a very, very convincing approximation of it. So for images, the most common way to do this is with what's called a bitmap. A computer basically takes a picture and lays a giant grid over it. Each tiny square in that grid is called a pixel. And then for every single one of those pixels, it just records a number that represents its specific color. And that gives us the basic DNA of any digital image. You've got the pixel, which is just that single dot of color. Then you have resolution, which is just how many dots are in the grid. The more pixels you have, the sharper and more detailed the image looks. And finally, you've got color depth. That's how many bits the computer uses to describe each pixel's color. The more bits you use, the more shades of color you can have, and the more realistic the picture becomes. And you know what? This same idea of chopping up reality into little measurable pieces applies to just about everything, not just pictures. It's how we capture sound and even how we track products in a store. When you digitize sound, you're doing two things. First, something called sampling. A computer takes thousands of measurements of the smooth analog sound wave every single second. Then comes quantization. For each of those little snapshots, it assigns a numerical value, which, of course, gets stored as binary. When you play it back, the computer just reconstructs that sequence of numbers, and our brains are amazing enough to fill in the gaps and hear a perfectly smooth sound. We even do this with physical objects. Think about the classic barcode. It's one-dimensional, just a series of lines that stores a short string of numbers. But the QR codes we use today are two-dimensional. They use a whole grid of squares to pack in way more information. But the coolest part? They have incredible error correction. You can literally damage or cover up to 30% of a QR code, and it can still figure out exactly what it's supposed to say. So now we have a new problem. We've turned our entire world into numbers, and that means we have billions upon billions of bits. A single uncompressed photo or a short video would be absolutely massive. How do we make any of this practical? The magic here is called compression, and there are two main flavors. Lossless compression is like a perfect zip file. It finds clever patterns to represent the data more efficiently, but you don't lose a single bit. You can always restore it perfectly. But then there's lossy compression. This is where it gets interesting. It strategically throws away bits of information that our human eyes and ears are pretty bad at noticing anyway. The result is a much, much smaller file. And the effect is just staggering. You can take a totally uncompressed image file that's over 1,300 kilobytes, and with lossy JPG compression, you can shrink it all the way down to just 5 kilobytes. That is a compression ratio of 275 to 1. It's an unbelievable reduction in size, and most of us would never even notice the difference in quality. And why should you care about this? Because compression is the unsung hero that makes the modern internet work. It's the reason you can have thousands of photos on your phone. It's the reason you can stream a movie instantly instead of waiting for it to download for 3 days. It is literally what makes our digital lives possible. So in the end, it doesn't matter if it's a voice changer app or a high-def movie. It all boils down to the same thing, a clever, highly structured arrangement of simple on and off switches. This secret language of zeros and ones has let us capture our words, our pictures, and our sounds. And it really makes you wonder, what part of our reality will we learn how to translate next?